Okay. Okay. So just to start off from wherever we left off yesterday. Before we just start off, just a quick question, guys. Yesterday we were talking about sampling and its basic concepts, introduction to sampling. Where are the, how is it sampled? Who are the sample like you know who is it that is sampling it, and why is sampling done, and so on. So regarding that, just a quick question. Are there any queries that or any areas in sampling that you would like me to address before we start off with our next level of discussions? So what we can do is that we can just have a quick round of discussion on that, and from there we can actually take it up. So in case you have any queries, feel free to ask me from yesterday's discussions. So I'll just switch on the screen and you can see the part that we had discussed, right? And then we can start off. Okay, so basically, in yesterday's discussion, we talked about the different basics of sampling, right? So, first, we started off by talking about what exactly a population is. Second, we discussed what exactly a sample is. Next, what we discussed was why do we need a sample, right? Then we discussed what are the different ways of sampling, under which we talked about purposive sampling, and we talked about random sampling. Within random sampling, we discussed about two types of models. One is a simple random sampling, and the other is stratified random sampling. And we discussed that why is it that we are using stratified random sampling in one part and simple random sampling in another, right? So why do we when is it that using stratified random sampling becomes important? When is it using simple random sampling becomes important? Now, after having said that, the next part that we discussed about it, what are the key strata, or why do we use why do we need stratas, right? After that, we discussed about that what exactly is the data, what exactly is the observation, and variable. So we discussed about observation exclusions and variable exclusions, and we said that these are the two reasons. So these are two reasons as to why a data or a subset of the data is made available, right? And when is it that a simple random sampling can be calculated, can be conducted most efficiently? So, following are some of the important areas that we have discussed about, right? Okay, so over here, what we'll do is, I'll just before moving on with the next part, just give me 5 minutes, and we will just recapitulate the key questions that can be asked, that can come up from this part. Okay, and what we'll do is using those questions, we'll just start creating out what should I say? Start creating out a questionnaire list, a list of questions, which we can refer to, or kind of a question bank, which we can actually use while preparing for interviews, right? So I'll just create a new sheet over here with all possible questions that might that this part that might come up from this part, right? So one quick question that comes out over here is, so question list. So over here, we'll just start reading out the question numbers. Okay, so over here is a serial number, and this is the topic, and over here we'll have the question. So as we come across the different topics, we'll start creating this question list, so that by the end of the module we have a decently long question list. talk to talk about, right? So first is from the start of sample, or rather, let me put it as sampling theory. So one very important question that comes out from here is that why is it that simple random sampling? Why would you require simple random sampling to be or why would you require the assumption of normality for simple random sampling? Why would we require the assumption of normality for performing simple random sampling? Right. So this is one question that we can that you can actually expect it during your interviews, and the reason is that without the assumption, right? So without this assumption, since it's a random sampling, for skewed distribution you might get biased samples. So for skewed distributions, simple random sampling can lead to biased samples if tail end values get sampled multiple times. Because since it's a since this is since when we are talking about simple random sampling and stuff, so what we are essentially talking about is uh, a random process, right? Now what would happen if suddenly so if there are tail ended values, right? So if there are tail ended values, so if there are tail-ended values, then if I'm using a simple random sampling, then I might end up with a biased sample. So that is one important question. The next question that comes out is then for a skewed distribution, how would you actually, how would you perform sampling, or if there is a skewed distribute, or how would you know that you need to that you can actually use simple random sampling? So how do you ensure that the population from you are drawing the sample is like it's a normally distributed population? Because in risk it is very difficult to get normal distribution, right? So in risk normal distribution is not observed, but simple random sampling is used. Why? So in risk, normal distribution for a variable is, or for a population is generally not observed, right? Then why would I use simple random sampling in risk? So because to ensure normality, to ensure homogeneity of the observations, segmentation is performed. Now from homogeneous risk profiles, simple random sampling can be. Simple random sampling can be done. So this is another question that might come up from the discussion that we have had yesterday. So this is also for sampling theory. Now comes the next question that we generally, so what we have said is that uh, we use samples, or the basic concept of sampling theory is we use to help us frame a representative sample for a population, because the entire population is not acceptable, or I mean is not accessible. So is sampling required Is sampling required in modeling exercises or in risk modeling? Because most of the data points, because in most of the cases, the entire population is available to the borrower, to the modeler. Now, how would you answer this part? So, because so if I have access to all the data points, given that say I am a banker, right? I am a person of the bank developing the models for the bank, then why do you think that that sampling will be is required in risk modeling if a modeler has access to the entire database? Then why is it that we are not using only the population, but we are again using a sample over here? Can anyone tell me the answer? You can put it in your chat boxes. So if I am working for a bank, say I'm working for Citibank, right? Now the I have all the data set, right? I have all the data set with all the historical data with me. I have the entire population. So why do we need the sample? Right. So basically, as Anirudh and Srinivas pointed out, the answer is right. So basically, the model developed will be implemented in the future, for which data points are not available. Therefore, in the broader aspect of time, in the broader aspect of time, the entire population is not available. Is not available. Hence, the analyst or the modeler only has access to a sample rather than an entire population. That is one. The second case is, the second reason is that all the observations and all the variables uh, questionless. So the second is that all the observations and all the variables may not be usable. So therefore, the modeler is only using a subset. And secondly is, and finally, the model cannot be used, cannot be developed on all the data points, on all the available data points. some of the points need to be kept aside for model validation as well. Therefore, the modeler only uses a subset of the available data points. Right. So these are the reasons as to why, you know, the what should I say? These are the reasons as to why the data. I mean, these are the reasons as to why this. So these are the reasons as to why we are actually using a sample, even if we always have the access to use the population. So these are the questions that has come up from my discussions yesterday. So if you think that there are any other important questions, feel free to address. Right. So these are some of the questions that I have addressed, right, which I felt was important, and hence I addressed them. However, if you feel that there are other important stuff, you just feel free to tell me the questions and we can actually jot it down. So the entire idea over here would be that at the end of the module we should have a good repository of questions with us. Okay, so this is just one part of it, right? So over here this is what we had discussed till the last class, that we are always using a sub part of the data, and that is why we have we are always using a subpart of the data, and hence we are always using a sample and not the entire population. Now next, coming to this third point that we had mentioned over here, talking about the concepts of model development and model validation. And the second part is model validation. So basically whatever data point is available to me, right, I cannot use the entire data point or all the data points for model development. I need to keep aside some set of data points for model validation. I need to validate the model. Now the question that comes out over here is that why is the model being developed? The model is being developed over here to test the robustness of the developed model. So how robust is the model over here, and how is it that it is actually putting it so how it is that it is actually, so how is it tested that it is robust? So the robustness of the model is tested using validation. And when I talk about this validation or this model validation exercise, so there are these two broad type of model validations that are there. One is called the out of sample validation, where you are actually breaking down data over a given period of time in two parts, into model development and model validation, right? So basically in out of sample validation what happens is so in an out of sample validation the number of observations only change, but the number of so the number of observations only change over here. So but what happens over here is that it is not uh, I mean the observations are different between model development and the validation sample, but the out of sample and the model development sample are defined for a data over same given period of time. And the third point that I have is out of time. The out of time validation is a validation exercise where you are actually validating your data in an out of time framework, right? So in an out of time framework, as in you are actually developing the model over a mutually exclusive period of time. So for example, if I have data, right, say from 2006, so I am just using this as an arbitrary example, right? So I have it from between 2006 right up to say 2008 010 for developing a model which we will be developing in the year 2011. Now what happens over here is that, say, this entire band of the data is divided into two parts. One is what I've done over here is 2006 say I have divided it between 2007 12. So this is the model development time frame. So I am developing the model using a data of between 2006 to 2007 12. So one thing that you can observe is that I am actually using a subset of the original data. Now, if I'm using a subset, then if you're thinking about this data over a span of time, you can say that yes, this is a subset of the original data, and hence it's a sample. So what we say over here is, so we call this to be the model development sample. So what we have is the model development sample, right? Now the next part that we have over here is the model validation sample or the model development sample over there, and this is called the out of time model validation. So that is between 2008 01 to 2008 12. This is known as a out of time validation sample. Right, so this is known as the out of time validation sample. So over here what we have, so what we see is that the overall data that we had, so using, if we have some in number of time periods, it is not possible for us to develop the model on that entire in sample period. We have to always use a sub part of it, right? And that is where we have the model development sample, right? from the model development sample, we is split into two parts. One is the development sample, and the other is the out of sample validation. So over here we develop this into test and training, or out of sample and out of into model development data, and into validation data, or as we call it, the out of sample validation. Right? So over here you see that when we are finally using the model, or when we are finally using the data, right, that is a sample. And now when I'm developing the model on one sample and like validating it on two other samples, right, then we need to ensure that these three subsets that we are creating are exactly representative, or they are more or less close to each other. Because if they are not representative, or if they on the overall, if they are not representative, then it would create a problem going forward, because by then the robustness of the model would become questionable over here. Hence, whenever a sample is to be, so whenever I'm creating the model development sample, I need to ensure that when the data is being split into model validation and model development, that is out of sample validation and model development data, it is there that the two data sets must be more or less similar in terms of the overall riskiness of the portfolio. So they must have the key criteria, the key categorical variables must be represented in a similar proportion in both these data sets, right? Okay, so Srinivas has a question over here. So let's just take it. Okay, so I'll take all the three questions. So starting off with Srinivas's question. So he asks that in this case, let's say we build the model, and when we validate it, if the models perform well, can we justify that this is a better model? Yes, so basically what we need to do is we need to ensure that the model predictions are working properly, right? So the model works properly on different data sets. So say suppose I develop the data, right, on 2006, so using data sets on the model development data, and I validate it on the out of sample validation data. So what am I actually doing? So both these data sets contain data from 2006 to 2007-12, right? So that means I'm just testing them on two mutually exclusive set of observations, but within the given time period. In out of time validation, what I am doing is I am testing the model in a exclusive, mutually exclusive time period, in a separate period of time when the model was not developed. Therefore, I am testing a model under two situations. One is within a given time period with different observations, and in the second case, I am uh, testing the model for a different time period which may or may not contain same observations. Right. So I am testing the model from both these aspects, because when I'll be implementing the model, right, I'll be implementing the model on a totally different set of values, a totally different set of accounts over at a different period of time. So I need to understand that if my model is used in a different time period, how robust the model remains. So if I have developed three models, and for each of the three models I'll do a out of sample and out of validation, out of time validation, and I'll see how the model matrices vary across, right, for each of the samples, and from there I'll be able to comment that which one is a more robust model. Clear? Srinivas, does that answer your question? Yes. So this is a very standard check that we do, right? So every model whichever is developed is validated, right? So you validate it on an out of sample data and you validate it on a out of time data. And that is, and it's not that either or, you have to do both. So whenever you are developing a data, I mean developing a model, be it a scorecard, be it a probability of default model, be it a simple loss forecasting model, whatever model it is, you need to actually test whether your model is robust, be performing on the out of sample data, and secondly, whether it is performing on the out of time data, right? So we need to do both these, and generally when we are developing models, right, we develop 2 or 3 models, right, and from there by testing for robustness we identify that which one is a better model or which is a better suited model. Okay, now coming to Kumar's question. So Kumar has a question: can development and out of sample validation data be the same? Yes, Kumar, they are essentially the same. Say for example, I have a data from 2006 to 2007 12. Now within that data there are say 1,000 accounts, or say there are 10,000 accounts, right? Now we will divide this data into a 70-30 division. So that the standard division rate is 70-30. So on that 70% of the observation, the model will be developed, and on the remaining 30% of the observation, the model will be validated. So the time frame over which the model is developed and validated remains unchanged. So it's the same time frame 2006 to 2007-12, but the set of observations in the model development data and the set of observations in the model validation data are absolutely different. Clear? And coming to Anirudh's question, when to use out of sample and out of time validation. So both out of sample and out of time validation are used whenever a model is developed. So whenever I'm developing a model, I'll use an out of sample and an out of time validation. Okay. So now the question that Kumar asks is, how do we segregate the data into a 70-30 ratio? Yes, we'll come to that. I'll discuss that later. But first, what I'm talking, so let's understand the basics first, then I'll come to how the split is actually done. Right. Great. So over here, what I'm actually trying to explore at this point of time is that why is it that even though we have the whole data with us, right? Why is it that I would need to do the sample? Why would I be actually working with the sample? Because this is a very frequently asked question, and people ask this question just to confuse you. So let's start off with sampling. So the moment you say that, okay, I divide my data into model development and validation data, and then we started working. So that is where they come out with a question that you already have an access to the entire data set. Then why are you using a sample? Why would you be bothered about creating 2 representative samples? So that is the point where you need to actually substantiate your explanation with these examples, right? So, so one of the ways that we saw that sampling can be done is simple random sampling with replacement and simple random sampling without replacement. So we saw that we saw the way how it is actually done. Now, the next thing that we'll talk about is we try to understand is that how is this division done. So I'm saying that so you have data from 2006 to 2007-12 which you are using for model development, and within that data you are creating 2 subsets, right? One is a model development data and the other is a model validation data or the out of sample validation data. Now the question that comes out over here is that why are you actually doing this split, right? So why are you actually doing this split? Now you are actually doing this split because of the following reasons. Okay. So now the question that comes out over here is that how do I split this data? So basically, when I'm trying to develop my model and doing an out of sample test or out of sample validation, what I'm essentially trying to do is I'm trying to understand. I'm trying to understand that if this model was invented within a given span of time, within the same given time period, but on a different set of observations, how accurate or how good my model would perform. So I will have a set of model performance matrices on my model development data. Then I'll have a set of model matrices on my model validation data. Then I'll check that how has the deterioration been like, right? Now from that perspective, what we need to do is we need to frame an understanding of how good or how bad the data is like. And that is where, so how good or how bad the model has performed. And that is where this out of sample validation concept of the out of sample validation comes in. So that means there will be a data set, right, containing some n number of observations. Say there will be a data set containing around 1,000 observations. Say 1,000 observations. What I want to do is I want to break the data into model development data. Say I'll break this data into 700 and 300. I'll break this data into two parts. One is 700 and the next is 300. So this will be my development sample, and this will be my validation sample. Right, so there is a model development data and there is a model validation. Now the condition that I need to ensure over here while doing this sampling is two things. Number one, the development and this validation data must be representative of each other, right? So they must represent the model develop the risk, the overall riskiness in the model development data and the overall riskiness in the model validation data should be very similar to each other. Now the second assumption that we need to keep in mind is that the number of observations between these two data sets has to be mutually exclusive, right? So there is 700 and there is 300, right? So so we need to identify the split. We need to identify the split into 700 and 300. and the two set of observations in these two data sets must be mutually exclusive. So the question that comes out over here is that how do I do this split over here? Because if I use that random sampling method which I had discussed over here, there is always a chance, there is always a chance that I might end up with, uh, you know, I might end up with double repeated values. Now, if I use a simple random sampling without replacement from that population, right? So when once I do it for model development and once I do it for model validation, right? So then I might, so both of these samples may contain same observations. So basically the idea is I pick out one sample, so 700 observations in this model development data, and the remaining 300 goes into the validation data. So over here, this when I create this thousand, when I create this, this development and this validation data, the suggested way to do this is to using simple random sampling without replacement. So imagine that I have a box of 1,000 observations, right? Now from that, what I'm doing is I'm putting my hand in and putting in an observation in the model development data. Then I take out one observation, put in the model validation data. One in the development, one in the validation. Like this, I keep on putting it on both sides, right? So after 300, I stop and the rest goes to the model validation data. Or what I do is I first randomly draw the 700, the remaining 300 move over to validation data. So that is the way we generally do it. Now this split using the data is often done using uh, by generating random numbers, right? So by the random numbers generated, they are just, so an interval on the random numbers are specified and the break is done. So how we do it exactly will on using the SAS platform, that is something we'll discuss when we go into the modeling side of things. Now our objective over here, our scope of discussion is limited to understand that how this split can be done. So over here, since I need to ensure that the observations do not repeat the observations do not repeat in the development and in the validation data, therefore this split has to be done by using simple random sampling without replacement, right? So over here, what we'll do is we'll use simple random sampling without replacement. Now, while breaking this data into model development and validation, right? Now, instead of using simple random sampling without replacement, we can also use the stratified random sampling without replacement. So basically, we choose a certain strata, and within that strata, from each of the strata, we sample out 70% and 30%. So if we are doing a stratified random sampling, say for example, I want to break my data into development and validation such that these products are one after the other. So basically, what you have is gold, silver, and what you have is platinum, and I require for 2% representation to go into each of the data. So I will sample out that 70% and 30% such that 2% of the total observations in the development data is like gold products, and 2% of the total number of observations in the validation data is also gold products. So if I have to do it, if I have to maintain certain restrictions on the characteristics between the two samples, then we need to do it. However, mostly when we are sampling it out, the delinquency factor is something important. So if you have a very specific delinquency distribution of the delinquency variable, then a stratified random sampling is used, right? Now, basically in risk, when you have a a structured risk data, there are a lot of different categorical variables, right, which have the representation, and just doing a simple random sampling may not give you a very representative model development and validation sample. Now, what happens is you can go for how do you finalize that whether you will be doing a simple random sampling or a stratified random sampling? That at all a stratified random sampling is required or not? Because if you are doing the stratified random sampling, right, and you are creating the strata for breaking it into development and validation, so when your model goes into implementation, that will also reflect in the code, right? So the code that the system has to maintain, the size of the code will also expand. So basically, you need to ensure that when you are suggesting a stratified random sampling, that is the best sampling procedure. So basically, for sampling, again, what we do is we use a champion challenger kind of an approach. So I use simple random sampling without replacement first and obtain the model results. I obtain the robustness stuffs, and then I do replicate using the stratified random sampling, and I check that. Now, whichever gives me a better robustness or whichever gives me a better representation of the entire population, that is what it is chosen. However, yes, stratified random sampling will obviously give you a better choice because it's a more granular kind of a random sampling which is done, right? So therefore, from this perspective, what we can clearly see is, or we will clearly say is that the entire objective of sample is not because you are doing a sampling because you do not have an access to the entire population, but rather you are doing the sampling because, right, because you cannot, because you have to, number one is because you cannot access the entire population, so the entire population may not be relevant, so you have to use a subset of the population, and there can be other issues because of which you may not access the entire population. So it might be that say for 3 specific months the data quality has been extremely bad, so you cannot use the data for that time, that point of time. You may have to remove that. So anytime you are, so a part of the population is not accessible to you. Now, even when you have a sub part of it, you cannot develop the model on the whole. You have to break it down into development and validation for robustness and for other model validation purposes. So obviously, at any point of time, because of these reasons, at any point of time, you are always working with a sample, and that sample has to be a proper representation of the overall population. Clear? Great. Any questions, Preeti? Any clarifications that you may want?
No, Tanmay, it's perfectly fine.
Great. Okay. So now the point that we have come up to is where we have talked about sampling, right? So I create a sample of a population. Now what? So now if I have created a sample and that entire population is not available to me, now what do I do? The next thing that I need to understand over here is, or the next thing that I need to think about is that what are, so now what? What next? So now I need to frame an idea about the population. About what population? About that population about which I don't have any bizarre kind of idea. The population which has not actually occurred. So that is a predictive model. So standing today, I want to predict that what is going to be, or are the borrowers who apply say next month onwards, or say 12 months on after 12 months, how likely are they to default? So basically, what I am essentially doing is I'm trying to predict a population about which I do not have any idea. But still, my objective is to frame an idea about the population based on the sample. So what I'm saying is that, man, this is what my sample is, this is what the historical behavior has been. And assuming that everything else remains unchanged and that no major shocks happen which disrupt the entire portfolio, if things were to go on the way that they are going on without any major disruptions, then my model has the capacity to predict that what should the average behavior of the borrower be. On an average, what could be the possible chances of the borrower to default? On an average, what should be the consumption of a particular segment or a particular group of customers. What should be the average purchases, or what should be the purchases that a group of customers are likely to make in the next 12 months, assuming that this has been their past purchase patterns, right? So models always predict basis history. So assuming that the average historical behavior continues into the future, my model should be in a position to predict like what is possibly happening in the next few months or in the next 12 months. Now, having said that, the next part of the story comes in like this. Okay. So basically, what I'm trying to do is I'm trying to always do some kind of a prediction. So, for example, no one knew before in 2008 or in the later part of 2007 that such a huge crisis was about to come up to India, right? So none of us knew that, and hence we were, and hence the models did not have the capacity to predict that shock. So when that shock actually came in and banged in, all the models had failed because there was a sudden disruption in the entire way the world was working. So generally, models do not have that capacity to do it, right? But and that is where I mean that is where all these new models are coming into place, where we call it the self-learning models. So whenever your the predicted error and the observed value that starts widening apart from whatever you had previously seen, the models start recalculating or recalibrations on their own, and they start learning from their own, right? So basically what happens is that uh, whenever the models realize that there is a departing error, that means what, that when the errors increase, prediction errors of the models increase, they run algorithms to minimize those errors over time. Now when we are saying all these stuff, right, whenever we are saying all these things, the next thing that we need to understand over here is that how is it possible, or that how is it possible, or when is it possible to frame an idea about the population based on the sample? So I can only do that if and only if there are no major disruptions, right, in what the past had shown and what the future has, or what the future looks like. So therefore, that is the part where the next question comes. Can we estimate the population parameters based on what the sample estimators are? So from here, once you justified why you need a sample, or that you need a sample, the next question that comes out is that why would you need a sample? What would you do with the sample? So is doing the sample a valid exercise? So the next question they ask you is, now I've given you the sample. Now what to do with that? So the answer to this is, using this sample, we look to predict the population parameters. And that is where the next question or the problem of estimation comes in. So this is where the problem of estimation comes in. This is where the next problem comes. There is a problem of estimation, right? this is where the problem, the next question of estimation comes. So the entire our main objective is to estimate the population parameters. Now the population, since the population is unknown to us, we don't have an estimate of the population. We don't know what the population parameters are like. So our objective over here is to frame an idea about the population parameter based on the sample, right? So that is where we talk about the problem of estimation. And if I talk about the point of estimation, there are a few important concepts, which a few important basic concepts, which comes up and which we need to address. So one of the questions that we need to address over here is undoubtedly what is population parameter. So what is the population parameter? Population parameter. The next part is what is an estimator, or what we call is a sample estimator. Estimator. Now, if I talk about an estimator, the next question that I want to answer over here is that what are the properties of a good estimator? What exactly is a good estimator? The next question that we ask is what are the properties of a good estimator? So what is it? And the third question that we ask is that what are the key types of estimation that we make in risk? So what are we trying to actually estimate in risk? Or in this risk, in this entire risk exercise, what are the key parts, what are the key concepts that we need to estimate, right? So that is something that we need to talk about next. So over here, talking about population parameter. Population parameter. A population parameter is an unknown numerical feature of a population distribution. So it's an unknown numerical feature. It's an unknown numerical feature of a distribution. Unknown numerical feature of a distribution. Right. Now the next part that we have over here is that if this feature is, so basically this is an unknown numerical feature, right? So I don't know what the feature is like. Now the next question that comes out over here is the sample. Now the next part is the sample estimator. Now the objective of the sample estimator is to frame an idea about the population parameter. Now what do I mean by the population parameter and what do I mean by the sample estimator? Let's take an example. Say an unknown numerical feature of a population distribution. Say over here is population mean. Now I do not know what the population is like, the population that I have today. Right? So I know that what I can tell you is then I'm just collecting a sample from the population, and from that population what I'm doing is I'm trying to frame an idea about the population mean, right? So the population mean and the population variance are unknown numerical factor, and this is represented as mu. Hmm. Now the objective over here is sample estimation. Now sample estimators is known as, or basically what are sample estimators? They are the known numerical feature of the sample distribution. So I know that it's a representative value using which I can represent the distribution of a sample. So now my objective is to use this sample estimator and frame an idea about the population parameter, right? So this is what the key idea is. Now over here, so basically say the sample mean that I have with me over there is x bar, is x bar. So what I want to know is that if the sample mean has the sample has a mean x bar, so based on that, can I say that the population mean is something similar or something close to x bar, right? So can I say that? So that is basically the question. Say for example, the sample mean is 96. So the population mean is 96. Now based on, and what I actually see over here is the sample mean is 95.6. Right. So based on this, what I say is that okay, the sample mean the power sample mean is 95.6. So let's do one thing. We can assume that the population mean is 96. So can I say that? So that is the big question. So if I need to draw this conclusion, so what are the conditions that must be there? The first assumption that must be there is that the population and the sample is symmetric. The population and hence sample is symmetric. Is symmetric. That's the first assumption. Second is that the estimator must be must be a good predictor or must be a good estimate of the population parameter, must be a good estimate. Must be a good estimate, right? So population hence sample is symmetric, so estimator must be a good estimate. Now if these two population or if these two characteristics are satisfied, then what we must do is, then what we can say is that yes, based on the sample estimator we can frame an idea of the population parameter, right? Now when I say this, the next question that comes up over here is the following. Now people say that now when I talk about a good estimator, what is it that I mean? What is a good estimator? So an estimator is said to be a good estimator if it satisfies the following properties. The first property that it satisfies is unbiasedness. So basically, a good estimator must be an unbiased estimator of the population parameter. So the next part that we talk about is unbiasedness. Unbiasedness. Right. Now the next, the second property that is there is known as consistency. So after unbiasedness, the next assumption, the next property that we have over here is assumption of consistency. Consistency. Right. Now the next part that we have over here is, so after consistency, the next property that we have over here is called the efficiency. The next part that we have over here is efficiency. One is unbiasedness, the other is consistency, the third is efficiency, and the fourth that we have is sufficiency. Unbiasedness, consistency, efficiency, and sufficiency. Okay. So we have these four characteristics. Now we need now, and whatever estimator we actually create, right? Whatever the estimator is that, and if it's a good estimator, then it must satisfy these properties. So what are these properties like? Now over here, if we start off, so whatever we'll say is that an estimator for us will be defined by theta hat. This is an estimator. And this is called the population parameter. So the unbiasedness, what unbiasedness says is a very simple thing, that the expected value of theta hat, the expected value of theta hat is equal to theta. Consistency says that an estimator theta hat will be said to be a consistent estimator for theta if theta hat tends to theta as n tends to infinity. Right? So if theta hat tends to theta, then I mean as n tends to infinity, then theta hat tends to theta, right? Now the next part that we have over here is the concept of efficiency, right? So efficiency talks about the fact that theta. So basically, see, if I have two unbiased and consistent estimators, right? So let's say theta had one. The next what we had is theta had two. Now in efficiency, its variance of theta had one. So variance theta one had is said to be an estimator, or it is said to be efficient estimator if the variance of theta one hat is less than the variance of the theta two hat. And the third characteristic states is that sufficiency. Now, what is this element of sufficiency that we are talking about? So, when I talk about sufficiency, sufficiency implies that the the theta hat must reflect all aspects of the distribution of theta. So, theta hat, say for example, theta is a function of, right? So say it's some function of the 1 delta 2 k. Now this implies that over here theta hat is like, so over here what we have is theta hat will also be some functions of the parameters, or some of the functions of which the parameter is explained by, right? So it's like this. So basically the theta hat will be a representation of the fact that, or it would be a representation that theta hat must reflect all aspects of the distribution, right? All aspects of the distribution of the population parameter. So these are the four basic characteristics. Now we'll take up each of these criteria and we'll start explaining each of them. Just before that, take 2 minutes and go through this. Yes, Kumar, we will come to each of these, right? So basically what I'm saying is, just in a nutshell, theta 1 hat is said to be an efficient estimator for theta 2 hat. I mean for theta, if between theta 1 hat and theta 2 hat, theta 1 hat has a lower variance. So an estimator with a lower variance implies what? That it has a lower fluctuation, and hence it is a better distribution, right? So we will come to that part. So we will take up each of these properties and we will discuss them in details. So just hold on, right? And then just let's just sit down, just think about this, and then we'll take it up. Okay. Okay. So let's start on this part. So talking about unbiasedness. So before we start talking about unbiasedness, right? Let's talk about something. Let's first start talking about the concept of expectations. What is expectations? We had discussed this, right? What is expectations? What is expectations? Anyone? We have discussed expectations, right? While talking about probability distributions, right? Yes. You can put it in your chat boxes as well. Okay. So expectation is nothing but the average that a distribution has. The average, right? But if I am talking about average, so it is not just a simple average, right? So this is for having expectations, you need to have idea about a distribution. to have an idea about the distribution. We need to have an idea about the distribution. So expectations is always connected to the concept of a distribution. That means if the very first property of unbiasedness talks about that for estimation you cannot just base things upon on one single sample, right? Okay. So basically, so over here, what we need to create over here is a distribution. So that is sampling distribution. So over here, if expectation is related to a distribution, therefore, while we are creating or when we are trying to estimate, so the estimation function, or whenever we are trying to create an estimation about the population based on the sample, we just cannot do it based on one single prediction or one single sample, and that is where we need to bring in the assumption of unbiased. I mean, that is where we need to bring in the concept of sampling distribution. So here we need to bring in the concept of a sampling distribution. Distribution. Is on the sampling distribution. So whenever we are talking about this distribution, the part or related to this distribution, right? So so basically, whenever we are trying to discuss about expectations, or whenever we are trying to frame this property of a good estimator, the first thing that with the base of this entire exercise, once I've created a sample, or I have a sample, and based on the sample I'm trying to frame an idea about the population, the basic part where this entire thing stands is the sampling distribution. So the first and the foremost part that we need to discuss even before any estimation is done is sampling distribution. And around sampling distribution, we do have an extensive set of literature. We have an extended literature around this, and there are a lot of these distributions that are there, right? So, however, we'll talk about the very basic part of sampling distributions. How is sample related to distribution? So how does sample and distribution relate to? So obviously, just let us recollect the concept of a distribution. A distribution is nothing but it is a listing of a set of outcomes and the relative probability. So a theoretical distribution on one axis lists the outcome, and on the other axis lists the probability of outcome. And an observed distribution lists the outcome and the relative frequency of occurrence, right? So this is what we need to do. This is what we need to look for. So over here, let us say that this is the population, right? Now I do not have an access to the entire population, and what I do is I'll just be collecting. All I can do is I can just access certain samples, right? So I have used my stratification or whatever sampling measure is there, and what I have done is I have created a sample. So this is 1 point x1. So this is a point x1 over here. Point x2. This is a point x3. Right. So this is a point x4, like this. So what I have done is I have created a sample of this. Let's just give me a second, please. Okay, so as I was saying, right? So basically, yeah. So we were actually discussing the concept of sampling distributions. So when we talk about sampling distributions, right? So say I created a sample over here by doing some kind of random samples or something. I created a sample over here. Now from this sample, what we do is we select out, we get a x1 bar, and over here, and we get a sigma 1 for this as well, right? Now, now what I say is that based on the fact that the mean of this sample is x1 bar, I can say that the population mean is also x1 bar. So I make this statement. But if I make this statement, then there is a challenge. Then I can be countered on the basis that this is only one kind of, there's only one random sample that you have taken. But what if I take another random sample and I get to see another figure? So how do I, collaborate it, or how do I reconcile the two? So that is the part where we need to do multiple random samples. And from each sample, so basically say over here, I created out one sample, right? So like this, what I also do is I create out another sample from here, right? So I create out another sample. I create out another sample over here. So from there I also get x2 bar, or rather let me put it as x bar 2 like this, right? Now similarly I create multiple samples like this, and once I have created all the multiple samples, now I look out for, I try creating the distribution over here. So what I say is that there are these samples, right? So I say that okay, there are these n distinct samples that I have created, right? And from each of these samples, what I also get is the x bar values. So the first sample I get x bar 1. For the second sample, what I get is x bar 2. For this, what I get is x bar 3. Like this over here, what I get is x bar 4, x bar 5, etc. Right? So these are the different ways through which we have actually. So these are the different sample means that have actually come up. Right? Now after this, the next part that we get to see over here is that for corresponding to each sample mean that we get, there can be a certain frequency. Say for example, this comes up with a frequency f1. This comes up with a frequency f2. This value comes up with a frequency f3, which can be as good as 1, right? So I can get 5 distinct values in 5 samples, or I can get certain repetitions. F4, or what I get is F5, like this, right? So now when we do this, so this table that I get over here with the value and this frequency. So for each of the samples, what I've done is I have found out the, so I have done a distribution check. So basically I have randomly sampled it out, right? Sampled out the X bars. Now what I get over here is the, this is called the sampling distribution of X bar, called the sampling distribution of X bar, of X bar, okay. So f over here is nothing but the frequency of X bar. Say for example, in the first sample, in sample 1, I have 3 observations, right? Say 10, 5, and 50. So all the 3 together will add up to 30, right? 30 divided by 3 is 10. 30 divided by 3 is 10. So this is from the first sample, or the first distinct value of the sample. Now in sample 2, what I get to see is it is 10 or say it's 20, 5. So this is 30. Again, the X bar over here is 10. So over here you see that 10 occurs twice, right? So this X1 bar will be 10 with a frequency F2. So this is nothing but the frequency. So over here what we have is the frequency and we have the output. So from this we can obviously compute the respective relative frequencies, right? So what we get is X bars and also a series of relative frequencies over here, right? So if I calculate it like this, if 1 by n, if 2 by n, if n by n. Right. So by doing this what we can do is, or by looking into this, what we can do over here is that can say that, okay man, this is what the relative frequency is. So we have the output and we have the relative frequency. So we have all the x's and we have the relative frequency. So if I now what I can do is I can actually plot this as a distribution, right? So I can actually plot this x bar on one side and the relative frequency on the other. So over here you can have your x bar and over here we can have the relative frequency. Right? So this is called the sampling distribution of x bar. Okay, so Srinivas has a good observation over here. He says that can we say that the relative frequency is the probability for that corresponding x1 or x2 or xn? Precisely, we can say that. So this is the probability from the observed distribution, right? So this is the relative frequency. The relative frequency tends to probability to the theoretical probability values obtained from a theoretical distribution as n tends to infinity. So this is obtained from the observed distribution. Now over here, if I compute the average of this distribution, then that is the expected value of x bar. So the expected value is nothing but the average, the relative frequency average of this distribution. So it is nothing but f1 by n x1 bar x bar 1 plus f2 by n x2 bar x bar 2. Like this, if I actually compute the long run average, so when I'm computing the weighted average, right? So then this is called the expectation. So the expectation of a random variable is nothing but the mean of the random variable, right? So this is what the overall behavior is. Right. So what we say is that if the expected value of theta hat is equal to the population parameter, so if we can actually prove that the expected value of x bar is equal to mu, then we will say that yes, this X bar is an unbiased estimator for the population parameter mu, right? So this is basically the idea of a sampling distribution, and the expectation of the theta hat can be computed from the distribution, right? From the sampling distribution. So we'll take a pause today. We'll stop here because and we'll start afresh with this estimator theory next week. And in the next week, we'll complete what estimation theory is all about. What are the properties of a good estimator? How do you calculate a good estimator? And from there, what we'll do is we will move into what are the different algorithms for computing good estimators, and from there we'll move into the concept of testing and hypothesis. So once we finish that, the next stage is to explore the different kind of testing, where we talk about t-test, mean difference test, f-tests, chi-square tests. So all these genre of tests, or these genre of statistical tests, right? So after that, we'll complete linear regression and logistic regression, bringing in relevant examples of risk. And once the statistical part is done, then we move on to talk about risk, product, scorecards, etc. Right? So initially, the exercise would be very theoretical in nature. So start looking up different materials, go through recordings. On YouTube, you have reading materials. I'm sharing these out so you can actually use these concepts, and you can create out your own notes, whatever you want. Any assistance with me, you sit down and you discuss it with me. I'll be uploading these recordings to YouTube as well, so you can access it directly from there as well. So we will by next week we will complete the statistical inferential part, right? So we'll have completed central tendency, the major descriptive statistics, probability theory, and inferential statistics, right? Then we'll talk about test procedures. Those will be the extension of inferential statistics, and from there we move on to talk about the predictive modeling techniques, right? And gradually, what we'll do is we'll start implementing these models or these parts into on SAS. The idea behind doing this part with with at this speed is to ensure that you are aware of every statistical concept when we start talking about risk, because risk is all about distributions. So we need to pull in all these information together, and from there we need to go into model development. Because if we do not do these parts prior to that, then when you start on with model development and you are in the midst of a code, all these parts will then then taking a download of these parts would become a bit of a challenge. So we would finish this part first, we learn how to implement them in SAS first, and then we'll take up the true core hardcore modeling, right? So at the end of this statistical portions, we'll start off with an assessment, right? So have a great week ahead, guys. I'll share this scribbler work, code work with you guys, right? Have a great week ahead, and let's meet next week. Thank you. Bye bye. Thank you for bringing a great audience.